This lesson will help you with the post-lab analysis questions for Le Chatelier's principle. When you're studying an equilibrium and you are attempting to increase or decrease the concentration of a substance in that equilibrium, it is possible that some side chemistry must be used. So what you need to do when you're looking at a substance that's been added is you need to decide if that substance is a substance that's in the equilibrium or if it's a substance that's going to react with something that's in that reaction. So for example, in the first part, you're studying the equilibrium of Fe3 plus thiocyanate ion going to the iron thiocyanate complex ion. In this, you added various things. The first substance that you added was FeCl3. And when you add FeCl3, essentially what you're doing is adding Fe3 plus, which is a substance that's in that equilibrium. So what you're doing is you are increasing the concentration of the Fe3 plus in the system. If you increase the concentration of Fe3 plus in the system, then the equilibrium will shift because this is a stress on the system. So hopefully you observed the shift that's appropriate for that increase in concentration. You should check your observations and they should make sense based on the predicted shift. Now in the second scenario, you added chlorine from KCl. So you added some solid KCl to the system. And when you look at that, there is no potassium and there is no chlorine in this reaction. So what that means is that the potassium chloride must be reacting with something in the equilibrium. And in this case, it's actually reacting with the chlorine. These two reactions are shown in your lab in the follow-up discussion area. Okay, this reaction of iron ions with chlorine ions and mercury with the thiocyanate. These are two special reactions and a new type of reaction that you haven't seen before. What you have is you've got the iron ions reacting with chlorine ions to make an ion. This ion here, in both cases, these ions are called complex ions. And a complex ion is formed when you've got this combination of items. One, you've got a transition metal. So in this case, you've got the iron ions. And the other item that you need to make a complex ion is what is called a ligand. And there are a few options for ligands, so we'll make a list here. So chlorine ions are possible ligands. Thiocyanate ions are possible ligands. Hydroxide ions can be ligands. NH3, ammonia, can be a ligand. H2O can be a ligand. I think that covers most of the most common ones. Now, a complex ion is a new concept right now, and the way that it looks in solution, if you've got this iron chloride, tetrachloride complex ion, essentially what you have is the transition metal in the center, and it keeps its charge, and then the ligands are attached, and we attach them with sort of dash lines rather than a complete line. So they're sort of loosely held to the surface of the metal. And this complex is an ion. It overall has a charge. So in this case, the Fe has a 3+ charge, and each of the chlorines has a -1 charge. So that's why overall this ion has a negative charge. the number of ligands that are attached to the metal ion, as a general rule, are double the charge. So this one here is not following the double the charge. In this case here, this complex ion is following that general rule, which we'll discuss in a moment. Okay, so in this particular example, we added KCl. The potassium in this case is a spectator ion. So really what we're doing is adding some chlorine ions to the solution. The chlorine ions reacted with the iron ions to form this complex. This is really the equivalent of forming a precipitate. When the iron reacts with the chlorine, it essentially gets trapped, and so it can no longer participate in this reaction. So what we're doing is actually decreasing the concentration of the Fe3 plus in the system. Okay, so that's the stress that has been put on the system, is that we're decreasing the concentration of Fe3 plus. And the equilibrium should shift appropriately, okay, due to this stress. Okay, so hopefully your observations and therefore the direction of your shift are consistent with Le Chatelier's principle. In the next example, you add thiocyanate, which is going to increase the concentration of thiocyanate. So if you add something that's already in the equilibrium, it's straightforward. It simply increases the concentration of that substance. In the last case, you added mercury ions from mercury nitrate. The nitrate are spectator ions, and the mercury ions form a complex. So this time, they react with the thiocyanate. So the mercury is the central transition metal. The thiocyanate are the ligands that are attached. And the complex ion that's formed here is mercury tetrathiocyanate. So these four thiocyanate ions are linked loosely to the mercury ion, which is in the center. And overall, this ion has a charge of -2. Like I said a moment ago, this particular complex formation follows the general rule of there being double the number of ligands as the charge. So mercury has a 2+ charge. The number of ligands is 2 times that, which is 4. And this is the complex that's formed from that. Okay, so with the mercury being added, what we're doing here, because we're complexing with the thiocyanate, we're actually decreasing the concentration of the thiocyanate ion. Okay, and that decrease in concentration is the stress on the system, and Le Chatelier's principle will have been followed. In the second reaction that you are studying, you're observing the shift using the yellow and orange colors of the chromate and dichromate ions. And you're looking at various scenarios. So you added some hydroxide and you added some acid. So those were the first 2 scenarios. And as discussed in the pre-lab, when you add hydroxide ions, those react with the H+. So it's a neutralization reaction. So what that does is actually decreases the concentration of the H+ in the solution. And Le Chatelier's principle should be followed from that point. When you add the nitric acid, essentially what you're doing is adding the H+. Since the H+ is an ion already in the equilibrium, the concentration of that will simply increase. For the next 3, what you were looking at was looking at the difference between adding barium ions to various solutions. So you had 3 different scenarios. You had the chromate ion, and you started with mainly chromate, and you added Ba2 plus. You started with mainly dichromate and you added barium. And then you started with a mixture of acid and dichromate. And you added the barium ions to that. Now what you are examining here is examining the effect of forming a precipitate on the equilibrium and what kind of a stress that can cause. So the key point here is that the barium chromate is insoluble in water, so it will form a precipitate, essentially trapping the chromate ions. And the barium dichromate is soluble in water. So adding barium in the presence of excess dichromate ions isn't going to form much precipitate. Now, when you look at each of these scenarios, in the first scenario, you've got a significant concentration of the chromate to start, and then you add some barium ions to that. So there are lots of chromate ions present, available to form a precipitate with the barium, and so a precipitate is going to form. As the precipitate forms, the concentration of the CrO4 2 minus, or the chromate ion, is going to decrease. So precipitate formed, okay, and it also decreases the concentration of CrO4 2 minus. Okay, so hopefully you observed that precipitate, and you also observed the shift of the equilibrium due to the decrease of the chromate ion concentration. In the second equilibrium, we start with mainly dichromate ions. There'll be a small concentration of the chromate ions present. So because of the small concentration of the chromate, okay, the precipitate will be formed. And in this case, although there's a small amount of chromate at the start, as the reaction proceeds and the equilibrium shifts due to the presence of the barium and the decrease of the concentration of the chromate ions, what you end up getting overall is still quite a bit of precipitate because this equilibrium will shift. As it shifts, more chromate is present. The chromate is present and available to react with the barium, so you get more precipitate. So it's almost like a chain reaction. Okay, as the equilibrium shifts, it precipitates, and it keeps shifting and keeps precipitating. Okay, so at first, although you may have not seen too much precipitate, if you leave it for long enough, it will reach a new equilibrium where there's quite a bit of precipitate formed. Now in that scenario where you start with the dichromate, the starting amount of chromate ions, or CrO4 2 minus, is going to be quite small. But there is still some present, so you are able to see the precipitate formed. In the last scenario, where you start with the dichromate ion, and before you add the barium, you add a significant amount of H+, so we add an excess of H+ ions. That equilibrium is going to shift very far to the left. Okay? Because of the addition of the H+, this equilibrium is shifting very far to the left, and it's lowering the concentration of the chromate ions to almost nothing. So we're forcing the equilibrium left, so we have a very low concentration of the CrO4 2 minus. Okay? And it's so low that when we add the barium, virtually no precipitate is seen. This is an example of what an industrial chemist might do. This equilibrium could be potentially a nuisance if you're trying to work with these ions and barium ions in the same scenario or the same container. Because as soon as this equilibrium gets established, and it's naturally established in water, then you're going to have some chromate ions present. And if you're trying to work with barium in that system, you're going to form a precipitate and you're going to end up with a big mess. So if we want to avoid forming the precipitate with the chromate ions, if we work with this in a highly acidic solution, okay, we can avoid the formation of that precipitate. Okay, so that's just a practical use of Le Chatelier's principle. In the last equilibrium that you studied, you had cobalt chloride, and this is another example of a complex ion. It's got the transition metal, it's got the ligands of chlorine, and it's overall got a charge. So that's one complex ion of cobalt. And on the right, we've got another complex ion of cobalt. This time, water is the ligand. Okay, so we've got an equilibrium between these two complex ions of cobalt, the chloride one being blue and the water one being pink. Now you warmed and cooled this reaction and you observed the shift of the equilibrium, and what you're going to do in your analysis is decide, based on the shifts that you saw with the temperature changes, whether this reaction is endothermic or exothermic. So essentially, is heat going to be a product in this reaction, or is heat going to be a reactant in this reaction? So you need to make that decision. A few key points when you are writing your responses for your follow-up questions. Okay, point form is completely acceptable and is encouraged. You need to make sure that you use proper terms such as increase the concentration or decrease the concentration. And you need to make sure that you include the charges on all of the ions. If you write Fe instead of Fe3+, you're not discussing the correct substance. So what I showed you here with increase the concentration of Fe3+, okay, that is an acceptable way to start an answer. So adding KCl, okay, decreases the concentration of Fe3+. You could write due to the complex being formed. So writing in point form is appropriate. Just make sure that you include the charges. So you need to answer the questions and you need to discuss 2 what-ifs for this particular experiment.